Hi, welcome back. This is Math with Dr. Claire, and in this video we're going to be working through some problems that involve finding critical numbers of functions. So we'll be doing functions in two dimensions, so like an x and a y, and we're going to do some examples that involve more complicated derivatives. So we're going to do a derivative that uses the quotient rule, one that is the chain rule, and another one that is the product rule. So we have three examples for this video. I'll talk a little bit about how we find critical numbers before we jump in. And if you want to follow along, I have my notes as a PDF as well as a blank worksheet in the description box if you want to check that out. Okay, let's jump into it. So we're going to be finding the critical numbers of functions. And so it's good for us to know what that definition is, like what is a critical number. So for finding critical numbers, I'm going to say that the critical numbers of a function, let's say that function is y equals f of x, so it has two variables, the input x and the output y. The critical numbers are values x equals a. So the critical number corresponds to an x value, and this value is a specific location where the derivative is 0 or undefined. So this will mean f prime of a, that's the derivative when we plug in that value, should equal 0, or the derivative does not exist at that point. So we're looking at x values where the derivative is 0 or undefined. That's what I'm defining as a critical number. So one thing to just note is that sometimes you'll be asked instead to find a critical point. So it really depends. I just usually ask students for the critical number. I think of the critical number as that x value. But if you see critical point, that's probably referring to the corresponding ordered pair. And that would be like an xy, or in our context, it'd be an ab. So what you would do is you'd plug in the a value, that's the critical number that you found. You'd plug that into the original function and see if you can find a corresponding b value. So this gets a little tricky because sometimes there might not be a corresponding b value, like it might be undefined. So this is really going to depend on your context, and that's why I actually like to just do critical numbers instead of critical points. But just something to note, we're just going to be finding the x value. If for any reason you needed to find the y value that went with it, you plug that critical number into the original function to find the output value that goes with it. All right, so that's a little overview. Let's get into the examples. So for our first example, we're going to find the critical numbers of f of x equals the square root of x squared minus 4. So okay, if we're finding critical numbers, we want to know where the derivative is equal to 0 or undefined. But something I really like to note is that I want to keep track of the domain of my original function. So the critical numbers are usually thought of as our candidates for the local maximums or the local minimums, and maybe even the global maximums or the global minimums. So we want to really think about how our critical numbers relate to the function we're starting with. The easiest way to do this is just to graph it with a graphing utility, so using something like Desmos or a graphing calculator to graph the function and then look at what's going on. But if you're having to do this by hand, it's just good to think about the original function, maybe think about the shape of it, but at least think about the domain, especially in these more complicated examples. So on all of these, I'm going to start by finding the domain of the original function just to help keep us with what's going on. All right, so let's find the domain of this function. With the square root, we need x squared minus 4 to be greater than or equal to 0. So solving an inequality like this can be kind of complicated to do it like formally correct. I really like to set it as an equality, make a number line, check intervals. That's like a lot of work. So I'm gonna just do this part quickly. Hopefully you can kind of believe me that this is the domain. We're more doing this to check, like this isn't a super necessary part of the process, but if you really wanted to be formal and good, this is a good thing to think about. Okay, so if x squared minus 4 is greater than or equal to 0, then x squared needs to be greater than or equal to 4, just moving that 4 over. And so if we look at this, we should notice that this means that we could use a positive 2, right? 2 squared is 4, and then any number larger than that would work. So 2 squared, 3 squared, 4 squared, or anything like that, anything larger than 2. So I know that from 2 to infinity is going to work here. But if I chose something less than 2, so like 1 squared is 1, that doesn't work. 0 squared is 0, that doesn't work. We can do all the way down to negative 2, but then when we get to negative 2, that starts working again. So this is like a little bit of my hand-wavy way of doing this. So hopefully you can believe me that if we chose anything less than negative 2, so that would be Negative 2 squared is a positive 4. Negative 3 squared is a positive 9. Because that squared makes it positive, these all work. So our domain is anything from negative infinity to negative 2, then from 2 to infinity. All right, so when we're looking at our critical numbers, we need to just remember this domain. So to find the critical numbers, we need to find the derivative. So let's go ahead and do that. We're going to find f prime of x, that's our derivative, and here we have a radical. So I like to change this to an exponent so that I can use a power rule, but I'm also seeing that we have a chain rule going on, right? We have a square root, and then we have stuff underneath it. So it's good to note that this is going to be using chain rule, and we're going to be then finding the derivative of what I'm writing as x squared minus 4 to the 1/2 power. So I'm just taking a second to rewrite it with an exponent instead of the square root. So we're taking the derivative of this, and now hopefully we can see why we need chain rule. The inside function is the x squared minus 4, and the outside function is the something to the 1/2 power, or the square root. So when we do this, we do the derivative of the outside function first, so that's the something to the 1/2. The 1/2 comes in front, we leave the inside alone, and we decrease the power by 1. So the 1/2 becomes a negative 1/2. Then we're going to multiply by the derivative of the inside function. Okay, so now let's do that derivative of the inside function. So what I have so far stays the same. And then I multiply by that derivative, so that derivative is just 2x. So the x squared, the derivative is 2x, and the derivative of the negative 4 is 0. All right, so now we just need to simplify. We'll want to set this derivative equal to 0 and see where it's undefined. So we need a more cleaner looking version of this in order to make it easier on us. Okay, so first I'm seeing the 1/2 and the 2 cancel. So that's great. We just have the x left on the outside. And then with that negative exponent, I'm going to bring it into the denominator so that it's a positive exponent. So I have the x, then I bring that entire term with the negative exponent into the denominator, and the exponent becomes positive. So I have x over x squared minus 4 to the 1/2 power. Now we can take that 1/2 power and rewrite it back as a radical. I think this will help us see what's going on a little better. So I have x over the square root of x squared minus 4, and this is my derivative. So we found the derivative. Now let's set it equal to 0. So let's take our derivative, x over the square root of x squared minus 4 equal to 0. When we do this, that whole denominator, in my mind, I can just multiply it over and it goes away. So if you think of a fraction, like when is a fraction equal to 0? A fraction is equal to 0 when the numerator is 0. So it's like, how many pieces of something do we have? I have 0 pieces, that would be equal to 0. So if the numerator, the top of the fraction, is 0, then the whole fraction is 0. So this is true when x equals 0, and this is our first option for a critical number. I am going to have us check them at the end, but this is a first step. So now we've found where they're equal to 0, let's find where the derivative is undefined. So this derivative would be undefined if we were dividing by 0, that would be bad, so we can't divide by 0. And it would be undefined if we were taking the square root of a negative number. That is actually a whole interval. We don't need to worry too much about that whole interval, especially since we already checked that in our domain. So we did that work earlier. Here we're really just going to focus on if we'd be dividing by 0. Yeah, because if we got a whole interval of answers, right, like those can't all be critical numbers. We really don't need all of that. So let's do the denominator equal to 0. So that would be x squared minus 4 equals 0. So we could square both sides, that's x squared minus 4 equals 0. Then we just solve. So we get x squared equals 4, and x equals plus or minus 2. Okay, so yeah, just be careful when you take the square root. It could be a negative 2 also. So from here, we're getting two options for our critical numbers. We're getting x equals 2 and x equals negative 2. All right. So I have my critical numbers of 0, 2, and negative 2, but I want to go back to the original function and just make sure these all make sense. So in a perfect world where like things were easy, we would just be done. We found the derivative, we set it equal to 0, and we found where it was undefined. We got 3 solutions, and cool, we're done. But I think it's really important to be careful here because a lot of textbooks actually won't count one of these as a critical number, which kind of makes sense. So if we look at that x equals 0, and we go back to the original function, x equals 0 is not in the domain of the original function. So if we were to graph it, this 0 doesn't even have a point on the graph. It's not an asymptote either. It's just kind of like an empty space in the graph because it's not in the domain. So we're actually not going to include this as a critical number. And unfortunately, there's not like a straightforward rule, I think, for this. I really think in every case you have to think about the function and what's going on and make a decision. So it's not just like, oh, it's not in the domain, I throw it out, because sometimes there's just like one value missing from the domain and it's a vertical asymptote and we do count it. All that nuance can be really complicated, so I suggest just going back to the beginning of each problem and seeing, does it make sense for this to be a critical number? And here, the 0 is just, I don't know, it's not in the domain of the original function, so I wouldn't include it. Some textbooks might include it as an answer, so this is probably a good idea depending on your context just to check. But for me, I wouldn't count this as a critical number. It's not like an endpoint of our domain, and it's not even on the graph. It's not like a relevant point on the graph of this function. So I'm going to throw that one out, but I will include x equals 2 and x equals -2 as my 2 critical numbers. All right, and there we go. So I do think this can feel a little like hand wavy, like there isn't a hard and fast rule about what's going on. And that really is because different people and different textbooks do this differently. If you're using the critical numbers to do some sort of first derivative test, a lot of this is going to come out when you do that. You'll be trying to check values, you'll see what's going on, maybe you'll graph the function or sketch a graph. But if we're just trying to define the critical numbers, it's good to go through this process, I think. Okay, let's do the next example. Let's find the critical numbers of g of x equals 3x squared over x minus 5. So again, let's start with the domain. I just think this is a good thing for us to do. So here, the domain is a little easier. We just can't divide by 0. So we need x minus 5 to not be equal to 0. And so that is x not equal to 5. So that not equal to 5, that's not our domain. And I'm just noticing that if we have only one value removed, if you remember anything about rational functions, this is a vertical asymptote of our function, and so it's actually quite likely that this is a critical number. So it's not in the domain, right? 5 isn't in the domain, but it's just like a single value that's removed, versus our previous example had a whole interval that was removed. So this is where it can get kind of dicey on what to do, but that's why I just want to comment it here so that we can keep that in mind as we're working. So if I was to write the domain as an interval, I would write -∞ to 5. I'm using parentheses to indicate that we don't use 5, and then I union that with the interval from 5 to infinity. So that 5 value, I can just tell you, spoiler alert, it will be a critical number. To me, this one's okay since it is on an endpoint of the domain versus just some random value in the middle. Okay, so if we're going to find the critical numbers, we need to take the derivative and set it equal to 0. So let's first find the derivative of this function. So if we're doing g prime of x, I can already tell we're going to need quotient rule. So we have a function in the numerator and a function in the denominator. This is a rational function. So we're going to need quotient rule. And let's go ahead and do that. So I remember this as low d high minus high d low all over the low squared, but however you remember it is just fine. I'm going to write it out now though. So we do the low function, the denominator, that's x minus 5. Then we multiply by the derivative of the numerator, that's the derivative of 3x squared. Then we subtract the derivative of the denominator, that's the derivative of x minus 5. And then it gets multiplied by the numerator, 3x squared. So low d high minus high d low. Okay, well, I guess I put those backward, but whatever. And then it's all over the denominator squared. So it's all over x minus 5 squared. If I was doing this on my own, I probably wouldn't have written out quite so many steps, but just doing it so hopefully you can see how the quotient rule works in case it's been a little while. All right, so let's do the derivatives now that we have left. So we have x minus 5 times the derivative of 3x squared, that's 6x. Then we subtract the derivative of x minus 5, which is just 1. That's nice. Derivative of x is 1, derivative of negative 5 is 0. And so we have minus 1 times 3x squared, and our denominator is still x minus 5 squared. I'm going to leave it like that. I don't think we need to do anything else with it, so I'm just going to leave it like that. All right, so remember we're trying to set this derivative equal to 0, so I do want to simplify it a little bit because it's going to help me make it easier to set it equal to 0. Okay, so let's distribute that 6x. I'm getting 6x squared minus 30x, and then minus 3x squared. And then this is still over my same denominator. And now we can combine like terms. So the 6x squared minus 3x squared, those are 6 and 3 of the same thing, so we're going to be left over with 3x squared minus 30x, and that's all over x minus 5 squared. All right, so now I think we've simplified this enough that we can set it equal to 0. So again, we're going to set it equal to 0, our derivative, and we're going to find where it's undefined. So let's do equal to 0 first. So this is the same logic we did in the last question. If I have a fraction equal to 0, this is the same as finding when the numerator is equal to 0, so the top of the fraction. So again, you can think of the denominator as multiplying over, and then it would go away since 0 times that is 0. But I'm just going to look at it as the numerator equal to 0. So 3x squared minus 30x equals 0. And now we have like an algebra problem to solve, which is cool. We have to remember our skills for that. Be careful here not to just move the 30x over to the other side and divide. We don't want to ever divide by x here because we're going to miss the option that x is 0. So just be careful on that. I'll show you what I would do. I would factor out our common terms instead of trying to divide by anything. So both of these have an x in them, and they both seem divisible by 3. So I'm going to factor out a 3x and see what I'm left over with. So 3x out of 3x squared is just x, and then 3x out of 30x is 10. So you can always check that if you multiply it back in. I'm getting 3x squared minus 30x, that's good. Okay, and now if we have two things multiplied together and they're equal to 0, it must be that one of the terms is equal to 0. So either 3x equals 0, or x minus 10 equals 0. And then these two equations will give us two critical numbers. So I'm getting x equals 0 from the first equation and x equals 10 from the second equation. And those are two of my critical numbers. All right, now we look at where the derivative is undefined. So if we have our fraction, that's going to be where the denominator is equal to 0. So we can't divide by 0, that wouldn't work. So we're looking at where x minus 5 squared is equal to 0. So solving that, you can hopefully see that it's where we have x equals 5. But if you want to go through the steps, we would take the square root of both sides. So I have x minus 5 equals 0, and then x equals 5 by moving that 5 over. So x equals 5 is where my derivative is undefined, and you'll remember that x equals 5 is also where our function is undefined. So since those are the same points, I guess, and since that value is like an endpoint of the domain, I'm going to be okay with including that as a critical number. So my final answers are x equals 0, x equals 5, and x equals 10. And we're going to include all of those as my critical numbers. All right, there we go. So we had 3 critical numbers for that. The domain wasn't super important, but I think it's good to just notice it and think about what the graph's gonna look like. Again, that x equals 5 is a vertical asymptote on my original function if you went to graph it in Desmos or something. Part of why I remember that is just because I've taught that class where we learned that recently, so it's fresh in my brain. But this is just sort of me giving extra commentary. I don't think this is totally necessary. It's just good to do in case you have a textbook that is really being picky about these sort of things. All right, so we have one final example. This time we're going to find the critical numbers of h of x equals e to the x times x squared plus 8x plus 16. All right, so we are going to do our domain again, but I don't think this one is too bad. So here, since we just have e to the x times a polynomial, so x squared plus 8x plus 16, I'm not seeing anything that could go wrong with our inputs. So any x value I could put into this function and it would work just fine. So our domain here is all real numbers, negative infinity to positive infinity. So this is nice. We don't have much to worry about when it comes to critical numbers. And often teachers will give you examples like this that have a clean domain when you're doing critical numbers, just to keep things a little easier. Unlike the other ones we saw that were a little more complicated. It really depends on your teacher. Again, I can just keep saying that every example. So our first step, as usual, will be to take the derivative. We'll eventually need to set it equal to 0 and find where it's undefined, but we can just start by taking the derivative. So we'll find h prime of x. And here I'm noticing that we have e to the x times a big term. So you could multiply e to the x into each one, but then you're going to have to do product rules on a bunch of them. So I'm just going to do one big product rule. I have e to the x times a polynomial. So with product rule, we take the derivative of one function and leave the other one the same, and then we swap. So derivative of f times g plus the derivative of g times f, that sort of thing. So let's take the derivative of e to the x first. That one's easy. So the derivative of e to the x, and actually I'm just going to write it out. It'll take some room, but I just want to make sure you know where this is coming from. So we take the derivative of the first function, leave the second one alone, and then we add it to the opposite. So I leave e to the x and I take the derivative of the polynomial, derivative of x squared plus 8x plus 16. All right, so now let's go ahead and do those derivatives. Derivative of e to the x is just e to the x, and then we can leave the polynomial there. So we are going to do a little bit of work with it eventually, but let's leave it alone for now. Then we have e to the x and we take the derivative of the polynomial. So the derivative of x squared is 2x, the derivative of 8x is just 8, and then the derivative of 16 is 0. So just little power rules on each of those. 2x plus 8 is that derivative. Okay, so before we set this equal to 0, I am going to do a little more work. Because I know that we're going to need to set this equal to 0, I really need things to look a little more simple, right? Like if you just gave me this, I'd be like, uh-oh, I do not know what makes this equal to 0. So let's do a little more work first. I'm noticing that everything has an e to the x, right? So the beginning part has an e to the x, the second term has an e to the x. So let's just factor that out. Then what I'm left with is just all of these algebraic terms. I don't know if that's the right thing to say. All of these polynomial terms. So I have x squared plus 8x plus 16, and then I add it to 2x plus 8. So I've just factored that e to the x out so that I can combine everything else together. You could multiply the e to the x in, combine them, and then factor it out, but I'm just going to factor it out first. All right, so let's combine like terms. I have just one x squared, so that stays there. Then I have an 8x plus a 2x, so that's 10x. And then I have 16 plus 8, which is 24. All right, so we have now simplified our derivative, and we have e to the x times the quantity x squared plus 10x plus 24. Okay, now we can get into finding where the derivative is equal to 0 and where it's undefined. So let's set it equal to 0 first. So I'm looking at this e to the x times x squared plus 10x plus 24, and I'm setting that equal to 0. So we used this logic in the previous problem, but if we have two terms multiplied together to be 0, one of the terms must be 0 in order for that statement to be true. So if you have two things and you multiply them and you get 0, one of the things must have been 0. So we either have e to the x equals 0, or we have x squared plus 10x plus 24. And I see this and I'm instantly like upset because I know that e to the x isn't 0, but just as a good check, it's good to think like what might I put in for x to get 0? And if we have e to a power, we're never going to get 0 out. That's like repeatedly multiplying e to the power. It's not just going to become 0. So this term doesn't give us any solutions. E to the x isn't 0, it's never 0. If you think of the graph, it's actually like always above 0. And sorry, with the mirroring, that might have gone the wrong way. But that means our other term is equal to 0, and that must be where the solutions are coming from. So we have x squared plus 10x plus 24 equals 0. So you could jump straight to quadratic formula if you wanted, but I made this problem, so I know this is going to factor. So let's factor this into two terms. We need two numbers that multiply to 24 and add to 10. So I see 6 times 4. 6 times 4 is 24, and 6 plus 4 is 10. So we can write this as x plus 6 times x plus 4 equals 0. And then we actually repeat the same logic, right? So one of these terms must be 0. So x plus 6 is 0, or x plus 4 is 0. And so we get our solutions as x equals -6 or x equals -4. And these are our critical numbers. So technically we do need to check where the derivative is undefined, but I'm noticing that there are no locations where the derivative is undefined. Any values for x work. I could plug in anything I want to this. It's just e to the x times x squared plus 10x plus 24. It looks a lot like what we started with, just with some different numbers slightly, and that had a domain of all real numbers. So here, this has a domain of all real numbers, the derivative does. I can plug anything I want in. So we don't get any results from this. So this means our critical numbers are the x equals -4 and the x equals -6, and that's our answer. So I guess I saved maybe the more straightforward one for last. That one wasn't too bad. We didn't have to check the domain. We didn't have any that were undefined. So all right, just remember, if your teacher or your textbook is asking you to find critical points, you may need to find the y value that goes with these x values. And to do that, you plug in these values to the original function. If you plug them into the derivative, you should get 0 or undefined, and that should be a little alert to you, like, oh wait, I was supposed to plug these into the original function. Most likely the values you get will not be 0 or undefined. They still could be, right? But if you ever need to find the critical point, take your x values, plug them into the original, and then you'll get the y value that goes with. So that is 3 examples of finding critical numbers. In each one, we looked at the domain just to make sure we had an idea of what the graph looked like. We found the derivative, and then we set the derivative equal to 0 and found where the derivative was undefined. And in this video, we did examples with chain rule, quotient rule, and product rule, which I think are the more complicated ones since you do have to do more manipulation to the derivative in order to set it equal to 0. That's it for this video. Thanks so much for watching, and I'll talk to you in the next one. Bye!